So today we'll focus on the mathematical processes, the models that are used to represent these patterns in space. And we'll focus on one benchmark category and then two special cases. The benchmark category is present everywhere in the literature, but in and of itself it's actually not that interesting, as we'll see. That is complete spatial randomness. And complete spatial randomness, as any randomness, is random. And you cannot model or explain random phenomena. It's pure chance. And then we'll see the two counterparts to this. One which is now referred to as aggregated spatial patterns. In the past it was often called clustered patterns. Aggregated is more appropriate. And then the opposite of clustered is regular spatial patterns. And so we'll see for each of these basically what they are, and then some formal mathematical models by which we can represent them and also simulate them. So there'll be several pictures of point patterns in the lecture today, and then in the lab on Thursday we will do this in R. We will actually, you will replicate the pictures that I'm showing you today. So we start with complete spatial randomness, or CSR as it's often referred to in the literature. And as I mentioned, this is a benchmark, a standard of reference. And it's a reference that is characterized by two major properties. One is uniformity, which means basically that each location has the same chance, the same probability of having an event occur there. So you look at a map of, say, our Buffalo city of Buffalo, anywhere in that city has the same chance of having a homicide. So that's the uniformity. The second characteristic is independence, which means that the fact that an event occurred in location A does not affect the probability of an event occurring in location B. And we'll formalize that a little more in a few minutes. So between these two, the uniformity and the independence, anything can happen anywhere equally likely, and it has nothing to do with anything that happened anywhere else. Now, there are not that many real-life processes that actually are like this. But it's a good frame of reference, and as in any hypothesis testing in statistics, you need a null hypothesis. And the null hypothesis is not really that interesting for its own sake, but the null hypothesis is there to be rejected, and to be rejected in the direction of an alternative. And the alternatives are really what you're interested in. And in this case, the alternatives will be the clustered patterns or aggregated patterns, and then the regular patterns. The formal mathematical representation of a process that is completely spatial random is what is referred to in the literature as a homogeneous, planar Poisson point process. Planar means it's in 2 dimensions. You can extend this readily to 3 dimensions, but we won't get into that. So basically, this is a process, meaning a mathematical model, that will tell you where in the plane these events will happen. Now, we already know where they will happen. They will happen anywhere equally likely. So we need something that can model that mathematically. We need that primarily as a benchmark, as a reference, to find situations where this is not the case. So a little more formally then, what is a Poisson point process? It is a special case of a Poisson distribution, which I'll get to in a minute, which is a description of rare events, of counts of events. A classic example is in the Prussian army is soldiers getting kicked by horses. So the number of kicks follows a Poisson distribution. Other classic examples are Lloyd's of London, an insurance company, how many shipwrecks there are each year. That also follows a Poisson distribution. Things like the number of patents, number of accidents, number of people with cancer in a particular region, they tend to be small numbers and follow the Poisson distribution. As the numbers gets bigger, the Poisson gets approximated better and better by just a standard Gaussian distribution. So you don't need to take that particular characteristic into account. The parameter of a distribution. Now, a distribution, as you know, is just nothing but a mathematical equation that summarizes the probabilities of different values occurring, or values in different intervals occurring. And rather than describing it as we did last week with a histogram or something like that, you actually put a mathematical equation that tells you the values between 2 and 5, this is the probability. Okay. So in order to model that, you need a parameter. The parameter that drives the Poisson distribution is the mean, is the average. And as it turns out, as we'll see in a second, for a Poisson distribution, the mean and the variance are the same. The mean is a central tendency, the variance is the spread around that tendency. For the Poisson distribution, those two have the same value. That's a very restrictive assumption, okay? Saying that the average and the variance have to be the same. That's very restrictive, and we'll see in a few minutes what it's called when that does not hold. So in our case, what we're interested in is the number of points that occur in a region. The number of points, and also later where they occur. Okay? The number of points is driven by, as we already saw last week, the intensity of the process, which is nothing but the average number of points per areal unit. So in order to be able to quantify processes like this, we need to put the points in a box, if you wish, and we need to agree on how big the box will be. That's basically what's going on here. So we're saying here the intensity is, say, 5 points per square kilometer, 5 homicides per square kilometer. That's less of an intensity than if it was 20 homicides per square kilometer. So this characterizes the process. And the second aspect, this is the number of events. The second aspect that we're interested in is, of course, where are these? And these are totally randomly scattered in the region. So then formally we characterize this by a Poisson distribution with mean lambda, the intensity, times the area. It's important to know what's going on here. This depends on the area. So for different areal units, you will have different means of this Poisson distribution. And to refresh your memory, I hope it's a refresher of your memory, mathematically, the Poisson distribution has this mean lambda times the area of A. The mean and the variance are the same. And formally, the probability density takes on this form. And it's a discrete distribution, so it's not continuous. So it's a distribution that gives you the probability that any discrete value occurs. So the probability you have no events in a specific area. The probability you have 1, 2, 3. And how you get that is by plugging the number of events, this y here in this expression, into the expression on the right-hand side. So you see y factorial in the denominator, and then in the numerator we see the intensity times the area, this is the mean, powered by the number of events, and pre-multiplied by e to the power minus the mean. So that's really 1 over e to the power of the mean. So the mean, or the variance, really tells you everything there is to know about the process. If you know how much lambda times A is, then you just plug it in here and take different values of y. You do this for 0, 1, 2, 3, and so on, and you have the full distribution. You know everything there is to know. A special case, which we'll use a lot, not so much today. Do you have a question? Not so much today, but when we start talking about the tests, is what is the probability that there are no events in a particular area? So for that, you need to have an area, and then you plug in this expression for the Poisson distribution, you plug in 0. So what is that going to give you? 0 factorial is what? 1. Okay? Something, whatever it is, here it happens to be the mean, to the power of 0 is 1. So all that's left is this here. So if you have the mean of the process, you plug it into e to the minus of the mean, that gives you the probability of having no events. And so in our case, what we'll be interested in is having the probability of no events in a given area. And an area that we're particularly interested in is a circle. And so to refresh your memory, we'll get to that in a second. Let me first show what the distribution looks like. So here we have, for a small mean of 2, you just plug in the numbers, and this is the characteristic skew distribution with a long tail on the right-hand side here. But as you up the number, you see it becomes more and more like a symmetric distribution. I cut it off here. There is a tail on the right-hand side, but it starts to look much more like your standard bell-shaped distribution. So as the average, as the mean of the Poisson distribution increases, it starts to look more and more like a Gaussian distribution, a symmetric bell shape. Or you could even say, if I ignore the tail here, I can approximate this central part very nicely by a normal distribution. So very large counts of events, you don't really need the Poisson distribution. Small counts of events, especially when you have zeros, then you do need the Poisson distribution. So let's get back to an example to make this a little concrete. We're interested in finding out what is the probability of finding no events in a circle. Because a lot of the statistics for 4-point patterns use circles. We already saw their use in the kernel density estimation, which is basically a disk that moves over the points. So in order to do this, we need two things. We need the intensity of the process, or lambda, which is expressed per unit of area. So in our case, I took the average from the Buffalo data, actually, 5 per square kilometer. And then we need to remember how you compute the area of a circle. And you check out some high school books and you find it's pi r squared, right? R is the radius of the circle. So if we have, for example, a tenth of a kilometer, 0.1 kilometer. So we stick that into this equation and we get an area of about 0.03. So what is the probability of getting no points, of having an empty circle of radius 1/10 of a kilometer in this particular example? You stick this in here. This is the area. This is the intensity. You figure this out, and it's 85%. So for a point process like the Buffalo homicide example, which has roughly 5 homicides per square kilometer, what is the probability using the Poisson distribution that we have no homicides at all in a circle of about 1/10 of a kilometer? That's 85%. Now if you up this, and the first time I calculated this, I put in, I think, 2 kilometers, then you'll see it's almost 0. So as you move out, as you make the circle bigger, this probability starts dropping very quickly because it's negative exponential, so it goes down very quickly. I think we should start wearing a helmet. I'm not happy with this. Okay, more formally, the Poisson distribution, it worked. The formal conditions for a complete spatially random process is, first of all, it has to be distributed as Poisson. Very important, and this may be subtle, but it's very important. Lambda has to be strictly positive. What does that mean? You have to have the possibility of something happening everywhere. For example, in Buffalo, we had all that water. We had the river and the lake. Unless you assume that homicides can happen on the lake. I guess you can shoot somebody in a boat or something. This is not valid. Okay. So you have to, when you analyze these processes, you have to make sure that the area that you consider is a realistic area where events can happen. If there are sub-areas where it's impossible for an event to happen, then you need to take them out. You need to mask them out because you don't want events to happen there. It's like, when you do population projection, spatial interpolation of population, and you get people projected in the lake and in the ocean, that's not right. So similarly, when you have areas where a priori these events cannot happen, in public health, for example, if you have census tracts that are primarily industrial, where nobody lives, then the probability of having people with cancer in that area is effectively zero because there's nobody there. In order to do your analysis properly, those areas need to be kicked out of the region under consideration. Otherwise, you keep a possibility that you're going to put events in places where they cannot happen. So, strictly speaking, we have a Poisson process with an intensity that is strictly positive. We have a region, an areal unit. It doesn't have to be regular. It just has to have a positive area. Then, as we saw, the number of events that happen in that region follows a Poisson distribution with mean the intensity times the area under consideration. So it's important to distinguish here, but in the notation, n of A with parentheses is the number of events in region A. These bars here, absolute value around A, is the area of region A. So the number of events is related to the intensity of the process and how large an area you're considering. I mean, that's reasonable. If you have a larger area, you'll have everything else being the same, more events in that area. And then we get our two conditions back that I mentioned in the beginning, but now a little more formally, the uniformity and the independence. And the uniformity means that for a given number of events, and we'll use this in the simulation in a few minutes, then for all practical purposes, the events, their locations, are a random sample from a uniform distribution. Uniform distribution is a distribution that assigns equal probability to all possible locations, or, in general, to all possible values. But here we're interested in locations. We don't have any values. It's not a marked pattern. So every spot in our area has the same probability of landing an event. And that probability is driven by this Poisson distribution. And the way it works in the Poisson distribution, I didn't put this in the slide, but conceptually, you might say, well, how do you get from this thing that's defined for areas to actual point locations? And mathematically, we get there by taking a limit and by making the area smaller and smaller and smaller. So then in the limit, we're dealing with probabilities for individual point locations. I didn't want to put that on here, but it's just a mathematical detail. And the second important consideration is independence, where we assume or require, if you wish, for a process to be completely spatially random, that there is no interaction between the locations. In other words, if you take a subregion A and a subregion B, two regions that are not overlapping, then there is absolutely no connection between the number of points in either of these regions. So the fact that you have more points in A has nothing to do with how many points you have in B. And that's very important because it takes out any interaction, any contagion. These are the kinds of processes that we're interested in. But in this benchmark process, we don't want them. We want complete independence. So how do we actually make maps that have these processes? And let me step back a second and tell you why we want to do this. We want to do this because many of the test statistics that we'll come up with are actually very complicated, and most of them are not tractable analytically, which means that you cannot just derive by taking derivatives and stuff like that what their properties are, what their mean or variance or asymptotic distribution might be. So we'll cheat. And we'll cheat by mimicking the process under the null hypothesis. And the null hypothesis will be complete spatial randomness. So it will be very important for us to know how to create processes that are completely spatial random. Because then we will want to compare some summary statistic for the process we actually observe, say the buffalo homicides. We will want to compare that to what that characteristic would look like or how it would behave if the process were completely random. So it's important that we know how to generate completely spatial random processes, and there are actually two main ways, there are several ways, two main ways to do this. One is to take the number of points as given, as fixed. So this is the case where we have buffalo, we have our homicides, the total number of homicides, or we have these juvenile locations in Cardiff, we have the total number of their locations. Now we want to put the same number of points on the map, but completely spatially random. And that's actually very easy to do. You just take a random draw on the x dimension and on the y dimension. So one way of generating a completely spatial random point pattern is to go to your random number generator and generate, say you want 20 points, get 20 x's uniform between 0 and 1, 20 y's uniform between 0 and 1, put them together and you have your points. Another way is a little trickier, and it lets more randomness into the process. Namely, rather than saying the total number of points is fixed, it takes the mean of the distribution as given, the mean being the intensity times the area. So like 5 per square kilometer. And then it allows the uncertainty of the Poisson distribution to generate different total number of points. I mean, it's a distribution, so you don't always get the same result if you draw from the same distribution. If you draw from a normal distribution, for example, with a standard normal with mean 0 and variance 1, you don't always get 0. You can get 3 and minus 4 and 1 and plus a half. These are all different outcomes. Same way here, if you let the Poisson uncertainty to really work, you will get a different total number of points each time you draw from this distribution. So that's one aspect of the uncertainty. Then the second aspect is putting those points, those NA points, on the map. And that's a little trickier. There are a number of different algorithms that do that. They're all variants of this uniform random number in x and y, but they make sure that certain conditions of the Poisson distribution are satisfied. And let me show you some examples of this. This is the first approach. So we take n as given, and these are all, to make it easy, put in a standard square. So the sides of this square are 1, the origin is 0, 0, the upper left corner is 1, 1. So these two point patterns are completely spatially random. And if you do, and we'll do this in the lab, if you do this again, you get a point pattern that looks slightly different, but has the same characteristics. The reason I want you to look at this for a while is that you might be tempted to say, well, this kind of a cluster here and this kind of a cluster there. Okay. Not so. This is as random as it gets. So what we want to do later on is devise test statistics that can tell real clustering from something that maybe looks a little like clustering, but in fact is totally random. So impressions of clustering can be given by totally random processes. What we will need is a device, a test statistic or a graph or something like that, that allows us to tell whether this impression that we get here is for real or purely due to chance. since we are drawing these points randomly, uniformly over the square unit square, they can land anywhere, which means they could land close to each other or not, with equal probability. But the fact that one lands here, for example, has nothing to do with the fact that the other one lands close to it, which is very different from some of the processes we'll talk about later, where there is an interaction between the location, and where the fact that one lands here increases or decreases the probability that another one lands close to it. Okay. So the difference between these two is simply the total number of points that we take to allocate over space. And obviously, as you up the number of points, this gets denser and denser. Okay. The second approach is where we set the mean of the process. This is per unit area, so we don't have to worry about this A part of the mean. So it's lambda times area of A. Area of A is set to 1, so we ignore it. This is 50, lambda is 50, and here lambda is 100. Now, one thing to notice is that the number of points that we generate is not exactly 50 or 100. Because as I mentioned a few minutes ago, we have introduced this extra randomness by drawing from a Poisson distribution with mean 50, and we get 53. We could have gotten 43. We could have gotten 70, but the chances that we get 70 are very small. But this is an extra variability that you introduce in the process. So in these types of simulations, we actually have two things that vary. One is the total number of points as drawn from a Poisson distribution with that given mean, and the second is where those points land. And again, if you look at this long enough, you may start seeing clusters or other regular patterns, and there aren't any. This is as random as it gets. Okay. This might give you a taste of how tricky it is to analyze point patterns and how tempting it might be to see patterns where there aren't any. And so one of the themes of these lectures is to get away from this I see that on the map, which you really can't. You see whatever you want to see. What you need is some standard, is some statistical test, is some numerical summary that tells you with a given degree of certainty, which is your type 1 error, your p-value, whether or not this is random. And that we'll see how to do next week. As I mentioned, complete spatial randomness, don't make too much of it. It's basically a benchmark. It's a reference point. It is a very rigid type of process. It's stationary. It's homogeneous. It doesn't change no matter how you turn it, rotate it, move it, whether you take a particular subset of the data or all the data. It should always be exactly the same. That's an incredible notion of equilibrium that we're imposing on this. As you look at the literature, the notion gets emphasized. This is not a natural process. As I mentioned last week, a lot of the early work in point pattern analysis comes from ecology. And ecologists are interested in finding out what are the processes that give us these particular patterns. You see a bunch of trees that are particular distances away from each other. How did they end up this way? Is this purely chance? Or is there some phenomenon that when one tree lands in a spot, it pushes the other trees away, or it attracts the other trees? Those kinds of processes are what we really want to understand. Look at disease. We find elevated disease in a particular area. We want to know, well, it's fine to be able to say it is elevated in this area, but how did it get elevated in that area? Did it get elevated through some kind of contagious process, or did it get elevated because there's a characteristic of that area that is different? Say, contaminated water, or poverty, or no access to medical facilities, which is very different type of thing and has very different policy implications than somebody moved in that had the virus, and so everybody else got the virus, which is a very different story. Same if you're looking at economic development and say the transmission or the spread of innovations. Are innovations spread by contact and by people interacting, or are they spread because the environment in a particular place is better at generating innovations than in other places? These are all the processes that are underlying. So we're really interested in what is called the inverse problem, and I talked a little bit about that last week, and I will again today, is how can we get from the pattern that we observe to this process that generated the pattern? And it's not always that easy. So complete spatial randomness was used a lot in the beginning, but lately there's been a lot of criticism of this as being something that really doesn't exist. So why focus on this? And as we'll see at the very end today, if I get to it, is the modern point pattern analysis, which is much more like regression analysis. Works in relative terms.